Hello and welcome back. Gaffer's here. I apologize for the full screen version of myself. I know it's not the best thing you want to be seeing, especially if you're seeing this first thing in the morning. But I have to kind of, I thought I'd come and explain a few things here. So this is episode 5. It's not episode 8. This is episode 5. So this is a rehash of a recording originally done for RSA in 2021. And I apologize. I fully intended to release it back in 2021, but things just got on top of me. So I was busy with all of my green card stuff and moving to the US and life in general during the pandemic, and running a company, etc., and closing it down actually. I apologize. This is delayed, but it is an interesting subject, talking about MAVLink. And the security or not of it. Just to kind of make a few things clear. So on the slides, my former employer stroke business was included on there because I was doing this during work time. But I'm no longer affiliated with them. If you follow me on the socials, you'll know I've got a new job and it's awesome. And it's kind of a dream job almost for me, so I'm loving that. But I'm no longer affiliated with this company. I did think about re-recording this episode, but I wanted to get it out as quickly as possible, along with some other episodes which are coming. So I've just kind of rehashed it for now, so that you have access to it and understand what MAVLink is. So like I said, there's going to be a couple more episodes dropping in a few days. One is going to be focused on the repairs to the drone, because it was damaged during transit. And I'm giving it a nice paint job so we can get some stickers on there. That's going to be an episode if you like the whole, building a drone thing. And the next episode, so that will be episode 9, I guess. Will be an episode which will go nicely in hand with this one. So in that one, I'm going to take you through the steps of actually hacking my drone, the theory of it, how it's going to be done, the tools, and how we build the tools. It's going to be a step-by-step process of how you take a spare telemetry radio, flash the firmware, and actually start hacking drones with it. And when I talk about hacking MAVLink, I know someone's going to come into the comments or mention this. I know MAVLink wasn't designed with security in mind. The decision was made that the security would be assured by the transmission layer, which is absolutely fine. But I do see it a bit like HTTP. HTTP was designed with no security in mind, and it was added on later with HTTPS. So, when you are hacking HTTP, you are still hacking HTTP. You're modifying it, or you're sending HTTP packets which, are not expected. This is the same thing. And this is the same concept with the MAVLink. Stuff goes in the clear, you can spoof, you can modify everything else. So, to those guys, to people who are saying, you're not really hacking the protocols. Well, I hear what you're saying, but yes, it is a problem. You go online, look at professional commercial drones for sale, and you'll see a lot of them with just this basic radio telemetry link on there. So they are vulnerable to these kind of attacks. So don't tell me it's not a problem, because it is. Anyway, so coming back to episode 9, like I said, we're going to go through all that. We're actually going to do the hacking. And the drone is coming to DEF CON 31, along with all the gear to do some demonstrations of the hacking and the tools to modify your own telemetry radio. So if you want to come along, watch the episode, flash your own telemetry radio and hack my drone at DEF CON, feel free. That's right. I'm inviting you to hack my drone at DEF CON. And what I'm going to ask you to do is obviously, take control of, of it, and to basically write some text with a flight plan. Upload a new flight plan, write some text on the screen, and we'll have it on a screen behind the drone. I will ask you to keep it clean. If you do anything dirty, I'm going to basically erase it, and if we find out who it is, you're going to be ejected. But There's going to be some swag and some prizes for you, for people who manage to do that, and to come along with the most innovative attack or message on the screen. So details of that will be in episode 9, but I just wanted to give you a bit of a taster before we go into MAVLink. So let's go. So this episode is part of a series that we are running in the Aerospace Village, looking into the security of UAVs, UASs, and drones. So in previous episodes, we have built a drone from scratch, including the electronics, configuring it, and we started flying it. And the goal is to also then look at how we can hack drones. All episodes are available on YouTube. This one will be eventually as well. And we've got more content planned for the rest of the year. So please, if you're interested, subscribe and stay tuned. So why are we taking a look at drone security? Well, this image from the FAA's concept of operations on urban air mobility helps explain the reason. So we have our rules of the air, which all aircraft must abide by, and these are governed in different classes of airspace. And then you have the airspace, which is governed for drones up to 400 feet and covered by regulations such as Part 107 in the States and Cap 722 here in the UK. What we have coming in the future, though, is a lot of interesting innovation going on in the air taxi space. Uber and Lilium, for example, are developing 2 very different vehicles for this market. Uber's going down the petrochemical route, and Lilium are going down the electric route. Both are fascinating. Both are really exciting concepts. And the idea is they're going to be used for short distances through cities, connecting hubs or connecting things like airports to offices, and giving that kind of value add to airlines, such as United Airlines, who have invested heavily in this market, to be able to provide that as a value add to their business customers who want to get from the airport to their meeting quickly and then back again, so they can put the kids to bed at night, on that return flight, after that return flight back at home. So what we have also is more commercial operations by drones. They're already being used here in the UK and in various tests in the States for delivering medical supplies as part of the COVID effort. So, and that is going to continue probably once the pandemic is over. So they're very good at connecting remote areas of the country, such as islands in the Highlands of Scotland here in the UK, or very rural parts of the United States, with the big cities where the medical facilities are. So if you need to bring a test or some medical supplies out to someone in a very remote location, drones are a very cost-effective way of doing that. They're also faster and probably more reliable as well. So what we have is this kind of conflicting airspace, because you've got helicopters, you've got air taxis, and you've got commercial drones all working in the same airspace, and obviously they need to be able to avoid one another. Drones will be pilotless, obviously, and air taxis initially will be piloted, but the goal is for them to be self-flying as well, although that's going to be a good 15-20 years away from now, I believe. So the urban air mobility concept of operations is to provide these kind of corridors through urban areas with routes down to the ground where they can land at homes, offices, or in tall buildings in the cities, or at airport hubs as well. So it's really important that we look at drone security and look at the ways in which either things can go wrong by accident, or whether they can be attacked to have an effect on the drone that the operator would obviously not want to happen. So I'm looking at MAVLink because it seems to be the most used protocol. Some manufacturers do have their own proprietary protocols, such as DJI. However, the majority now and probably in the future will be using MAVLink. And it's used
mostly in, well, its intended use was for micro air vehicles, like it says in the name. However, it's been adapted to be used in all types of vehicles, whether they be on sea, on the land, as well as the air, and even robots as well, because it's a very lightweight layer 2 protocol, which allows lots of data to be sent on a fairly long distance. I'd say it's longer than Wi-Fi or Bluetooth can, in a reliable manner, and it's used to as a comprehensive set of messages that allow for monitoring, instruction to be sent, but it also allows for a route to the internet as well. So if your autonomous vehicle has a sensor on board, say for example LiDAR, which it might use to map the ground to avoid terrain, but it can also be used to send that data to the cloud in order to generate accurate 3D mapping of areas if that is your goal. And I know there are organizations such as Ordnance Survey here in the UK who do that. So MAVLink is most commonly used using SICK 3DR radios, and they're on 433, 868, 915 megahertz, depending on your location. And the maximum rate is about 250 kilobits per second. Now, the thing with that is, though, as you increase the distance away from the ground station, you probably have to reduce the baud rate, so you have to reduce the speed down in order to get the fidelity of the signal that you need. So I'd say maximum 250 local to where you are if you're within 100, 200 meters, but as soon as you get to 500 or even more, as long as you have the authorization from your regulator to do so, then that throughput will probably go down. And the typical range of the off the shelf of these radios is about 300 to 500 meters. Although if you're starting to use a directional antenna, if you've got a Yagi, and even if you stick on a servo, which using the feedback from the ground station, you can use it to say, well, here's the angle to the drone, point the Yagi in that direction. You're probably going to get a lot more than that. I've heard of people with just the basic 100 milliwatts radios getting pretty decent distances. And I reckon if you get the authorization to fly further distances than 500 meters, and also the authorization to use a more powerful radio in that spectrum, then you could probably get some serious distance indeed. And like I said earlier, it's got a route to the internet, so it has a network interface, and you can stream the MAVLink through IP with using both UDP and TCP support. So really interesting concept, but there's some issues, and we'll come on to those in a bit. So there are two versions of MAVLink. There's version 1, version 2. Version 2 is obviously an upgrade to the first one, and they both have their strengths and weaknesses. Starting with version 1, there's an identifier at the start called STX, and for version 1, that is basically binary FE, and version 2 FD. There's a reason why they didn't use FF. Obviously, that's 255, and that could get confused with other things. The next marker is the length, and that's the length of the message in bytes. Next one is a sequence identifier, and that's between 0 and 255. Once it gets to 255, it loops back to 0. So system ID, and this identifies the drone to the GCS. So you can actually, with a ground control station, you can control multiple craft at the same time. I think it defaults to 1, and you can actually, you can use multiple crafts at the same time. This might be useful if you're an operator and you're doing multiple drones at the same time. You can keep control of them, keep track of them whilst they're flying. Or if you're maybe in a club, if you're a club flying drones around in a local area, you need to be able to prove that your drones aren't, leaching out of the authorized airspace that you've been granted by your regulator. Then a ground station with multiple drones might be a good way of doing that. So you've basically got a track through the ground station that you can then provide to the regulator as proof that you're abiding by the rules of your club. The component ID, so this identifies the component sending the message. So what you're not going to get is, one frame, one MAVLink frame sending data for everything. It's basically, the GPS might say, right, I've got to send my location. Time is up, I've got to send my location, and it's going to send it through a MAVLink. So it's going to say, drone one, system one component, for the GPS, and then it's going to send the the message type with message ID is the next one. So 0 is a heartbeat. That's sent every second, and that's important later on. And for if it's a GPS MAVLink frame, then it's going to be message ID 33. Then comes the payload, a maximum of 255 bytes. If it's longer than that, then I have seen them stringed over multiple frames. How they identify that, I'm not quite sure yet. I haven't quite gone into that much detail, but I have seen it in the data that I've seen. And then finally, you have a checksum at the end, which is a CRC16. It's 2 bytes with an SAAS4 hash, which is seeded as well. Version 2, this is the same as V1, but there's 3 or 4 significant differences. There are incompatibility flags, and these affect the message structure. So basically, if your system cannot interpret the flag, then it cannot handle this packet. So incompatibility flags are basically indicators that the structure must be understood in order to be used. If it can't be understood, then that the whole packet is basically disregarded. And incompatibility flags, they don't affect the message structure, and they can be ignored by the system if they can't be interpreted. So that's the key difference there. They come into play certainly when the packet is signed. So the incompatibility flag of 1 means the packet is signed, and compatibility flags, could be things like high priority messaging. If you don't understand it's high priority, it doesn't really matter as long as you've got it. And different software might be programmed different ways. So those are those 2 there. Message ID obviously is the same sequence, same order. It's just before the payload, but it's bigger. So instead of 8 bits, it uses 24, which gives you over 1.5 million different types, which I'm pretty sure they'll never be able to fill. I'm not sure why they went that high, but I'm sure somebody's got an explanation. And then the key difference with version 2 is the signature frame, which is optional, but obviously highly recommended. And what you do is you basically have a pre-shared key between the ground station and the drone, and that is then used to generate the signature in the following format. So you've got 1 byte for the link ID, which is the channel on which it's been sent. That could be radio, could be Wi-Fi, could be Ethernet. You've then got a timestamp, which is in 10 microsecond increments since January 1st, 2015. Interestingly enough, if you get, so this timestamp has to increase by 1 every time. It can't be the same. So if you get more than 100,000 messages in 1 second, you could have a case where the timestamp is ahead of real time. Just something to bear in mind. And then you have the signature, which is based on the entire packet, less the STX frame. The timestamp and the secret key all used together to generate the signature at the end. Only 6 bytes. So it's not that big a signature. So talking about MAVLink weaknesses, starting with version 1, obviously the checksum is easily calculated. There's no authentication or encryption in the packet. So, and given that the checksum is based on the whole packet less the STX identifier, it would not be difficult to spoof a message. So, you can basically just go, here's what I want to send. Here's a valid checksum. Send it up. There's no authentication. So the drone or the ground station is going to accept the message if it's received. With version 2, again, there's no encryption of the packet. There's just the signature. So the secret key could be reverse engineered. The signature itself is not that long. It's only 6 bytes. So there's enough. There's not enough entropy really to avoid reverse engineering of that key. And those of you who've seen the imitation game will know that there are certain messages which repeat frequently that could be used to generate or to identify patterns. So think back to Enigma and Christopher being used to crack it. Well, there was a certain message. I'm not going to say what it is because I don't want to get told off. But there's a certain message every day at 7 a.m. So the story goes anyway. And that was used to crack the key because they knew that message was going to be the same every time, every day. So once they figured that out, they could then reverse engineer the messages for the whole day. And I think the same thing could be done here because you've got certain things like the heartbeat messages, which are sent every second. They're a fixed size, and the only things that change are the increment number and the signature itself. So, the payload is going to be fairly similar because even though the payload is sent by the flight controller to the ground system to say, well, I'm in this flight mode or this, that, and the other, they don't change very often either. You might change from RTL to stabilize or to autopilot or whatever, but you're going to have multiple messages because they're sent every second that are going to be the same. So you're going to have that, high frequency of messages that can be used to, basically find patterns and break that entropy. But also, you're also going to need, for both versions, you're going to need a stronger RF than the source. So you might have to be in between the drone and the ground station and have a stronger signal, of course. You may even need to jam the GCS or the drone in order to have the effect that you want. But, physics doesn't lie. Physics is physics. If you point a stronger RF at a receiver than the source, the receiver is going to pick up your signal rather than what it should be. So this heartbeat packet, it's sent from the drone to the GCS, and the GCS also sends them to the drone. They are the most important packets. They are sent every second, and they contain various static flags, flight mode, message ID, and they're very easy to reverse engineer. That's to be used to reverse engineer that secret key. So based on this, then, what threats can we have? So looking at the the CIAA, I think it is now, the cube rather than the triangle. So confidentiality or privacy, the messages aren't encrypted. So eavesdropping is easy. And once you start eavesdropping, well, you can start doing all sorts of things like identity spoofing, which can lead to unauthorized access. Or you can just do traffic analysis. Very similar to the way people that use Wi-Fi pineapples to see if the same person carrying the same mobile phone is coming past them, on a regular basis, and looking for patterns. Well, the same thing can be done with MAVLink. And then there's availability attacks. Like I said, we could do some jamming, but we could also, DOS or flood the ground system or the drone in order to have an effect. We could either, flood it with legitimate messages that would overload the ground system or the drone, again, to have an effect, or we could deny the service in sending, packets which are constructed correctly but are just gibberish, and then the system just is unable to handle it. We could, we could do an authenticity attack, so we could spoof the data going through. So if the drone is being used, like I said, for mapping, we could inject our own data into that mapping data. Or we could, spoof the GCS as well. And then we get into the integrity attack. So a man in the middle, where we, instead of completely taking over the drone, we might just want to have an effect like temporarily change its course, hijack it, send it a new flight plan and get it to fly where we want it to be, grab it with a net or fly it into the ground so we can steal the camera. Bearing in mind that some of the cameras on these drones are thousands and thousands of pounds. So whereas my drone has probably cost about £1,000 to build, if I was to put a high quality camera in there, it would probably increase the price by about 5 or 10 times. So, the drone is probably not the target in theft. The theft might be the payload, which could be an expensive camera, or if it's, say, a drone delivery, then it could be a high value item. And, if you're sniffing data and you might want to replay it in order to have an attack on the drone, again, it would be easy to do because that data is legitimate. It might be out of sync, but the drone or the ground station may think, well, I've just missed some packets out, and I'm going to take this data as real. And then, of course, we could do message modification, position spoofing. The possibilities are endless, all because of the lack of protection on this protocol. So I've been looking at the MAVLink packets themselves in the wild. So here is a screenshot from my ground control station, which is showing the heartbeat packet. There's a MAVLink inspector on there, so I can inspect the data being sent through. And this is the vehicle one, which is the drone. And this is the heartbeat that it's sending to the ground control station every second. We can tell it's every second because it says 1 hertz and it's 17 bytes per second. So that gives us some helpful tips on looking for it. I did actually start looking at the actual RF sniffing on this one, using an SDR. It is possible, but because of the frequency hopping, it does make it more tricky. So I decided just to do some sniffing on the USB interface instead, just to make it easier. The idea is to show you that it's possible rather than actually going fully through with it. The goal is to do that in the end, but I was just running up against time. So looking at the FTDI packets being sent through, here is the payload, which has been received there. As we can see, FE, that's our STX there. And then it goes through length 95200, heartbeats. Excellent. So that's what we want to look at. FE254 MAVLink V1, 9 bytes long. The sequence number, system ID allocated number 1. We saw it was vehicle 1, so that's right. Component ID, autopilot, great. And then 00 heartbeat. And then the checksum at the end there. And then we look at the heartbeat payload. Interestingly, this should have been 00 at the beginning to denote, a generic air-based drone, and it's got 0 alpha, which is a ground rover. Now, I have accidentally crashed my drone recently, and that could have caused some issues. I'm not quite sure why that's showing 0 alpha, but I'll have a look into it. And then we've got, the next byte is 00. That means generic autopilot, 00 disarmed. It was disarmed at the time. And then we've got the custom mode. And these relates to the GCS output. So we got 013, 217. They relate to the fields in here. Interestingly, obviously it's showing system status 5, which means critical. Means it's not in normal mode, but it can navigate. That's probably because it's disarmed. It can't see the radio controller. There's a few other things not fully plugged in, the motors, for example, because the wings were off. That's probably, I'm not too worried about that one. And then this MAVLink version 3 is a fixed value that never changes. And then if we look at heartbeats going the other way, so this is vehicle 255, that is always the ground station. And then we've got the heartbeat there. Again, 1 hertz, 1 per second, and 17 bytes per second. So it's a packet that's 17 bytes. And here it is, 17 bytes transmitted. Starts FE, that's my STX, 09, that's 20, that's 17, brilliant. So this is the packet. And we look again, we've got the right thing, sequence ID. So system ID 255, that's the ground system, that is the ground system default value. You can change them, but that's just the way they are by default, and that's the way I've kept them on mine. Component ID 190, it's from Mission Planner, 00 heartbeat, then the checksum at the end there. And then the heartbeat payload, 00, generic micro air vehicle, that one's correct. So what I think has happened is that I haven't pushed the parameters from the ground system to the drone since the crash. So that's probably what I've got to do to reset the heartbeats from the drone back to the ground system. And there we go, same as the others, it's disarmed, which is good. And then the autopilot mode, base mode, etc., all correspond to the GCS output there. And then 00, uninitialized, state unknown, that's because the drone hasn't been kind of armed or disarmed, or basically the ground station is saying, I don't quite know what's going on here, so it's saying uninitialized. So obviously these are heartbeats for version 1 because that's what I've set up my drone to use. But if you think back to the construction of version 2, then all you're going to have is a couple extra flags and the signature attached to it. And given that these heartbeat payloads are otherwise exactly the same, and those fields are going to remain always the same, then this is where you're going to be able to turn around and say, well, actually, the only thing that changes is that sequence ID and the signature. So you get enough of these packets, you're going to be able to reverse engineer that secret key pretty easily. So there are a few countermeasures that we can look at implementing. The first one's the hardware. Now, we've got possibility of using FPGA. These are fantastic, very highly customizable, high throughput, circuit boards. They're fantastic, but they are heavy. They are also very power hungry, and these are not conducive to a long flight time. So they're not really a realistic solution for drones. Another idea I saw floating around on some research papers that I was reading, one was the use of a Raspberry Pi. And that's been set up as an alternative channel for when a drone is taken over. And what the drone is programmed to basically take priority of the Raspberry Pi stream over the 3DR stream. And then basically, if anyone starts doing some RF attacks and takes over the drone, the ground control station switches to the Raspberry Pi route, and the drone then is taken back over by the legitimate operator, and it saves the day basically. It also allows the data stream to be encrypted, but both of these basically induce a lot of delay in the system. So whereas with 3DR the response times are pretty fast, not immediate, but you're talking a couple of milliseconds. With the Raspberry Pi, that goes that delay is increased significantly. So not a real safety issue as long as you're aware of it and you know how to handle it. One thing I have thought of is if you could implement, say, a very lightweight Raspberry Pi to basically have a preset message which reprograms the flight back to base. So and what you could do then is instead of having that delay, you just basically say to the Raspberry Pi, send your data to the flight controller. The flight controller goes, okay, I'm going back to home, and saves the drone from being lost or stolen or crashed into the ground or into a building, depending on what the intent of the attacker is. I might do that on my drone later on. We'll have a look. Some other countermeasures are software-based. There's something called SMACM Pilot, I believe, SMACCM Pilot. And this implements the GIDL protocol with AES and symmetric keys. It encrypts the payload, the header, and the CRC, which obviously has an overhead to it. Being symmetric, it's not ideal either. There's another protocol in the works, SMAVLink, which is basically secure MAVLink. Again, that's GIDL protocol with AES hardware, but it encrypts the payload only. So the rest of the message is still in the clear. So it depends on what your risk is. So if your risk is the drone or is your risk the data, in which case, you might want to choose one over the other. Also, it depends on, the encryption of the payload. If that is strong enough, would that basically make the entropy of the signature go up to a level whereby it's too difficult to crack, the secret key in order to, spoof the messages? That would be interesting to look at. It's not implemented yet. It's not available yet. But when it comes out, I'm sure we'll be having a look. Further software countermeasures, RC5. It is lightweight, but it does need enough rounds to ensure security. They recommend 18 to 20. But I think this is a good solution. It's a good possibility, depending on your hardware and software, of course. And another one is the Caesar cipher. However, it does send, the Caesar cipher sends the unencrypted key as part of the handshake between the drone and the ground system. So if your attacker is within range during the startup of the system, then he's going to be able to intercept that private key or an encrypted key when the system is switched on, and be able to, and then basically, your whole connection is compromised. So I don't think that's probably quite feasible. Although that said, I know in aviation there's a lot of trusted zones, especially when it comes to networks. Whether that applies to over-the-air networks is debatable. But it might well be that you could prove that an area is safe from interference, or from being from the data being intercepted. If you could prove that as part of your authorization, then maybe that could be used. Like I said, it's a possibility. I would probably lean towards RC5 at the moment, though. So, like all things in RSA, we have to look at how you're going to learn from this. So we have the apply slide. And this really only applies to drone operators. But so in this session, we've touched upon the weaknesses present in MAVLink that exist currently in V1 and V2, potential attack scenarios which could lead to consequences. So if you're a drone operator, then you really need to start looking at how these weaknesses apply to your operating model and the technology you use. Obviously start looking at identifying your key assets and identifying those threat scenarios and the actors and the intents that they could have on your assets. And then take that information and look at where you are vulnerable, whether it be through MAVLink, whether it be through other parts of your system. Bear in mind that MAVLink is not the only way to attack a drone system. It could be the ground control system is a standard build, has not been hardened in any way, has got no antivirus, and it's got an open connection to the internet with no firewall. Well, in which case, you're probably vulnerable to network attacks as well. So you need to assess where you are vulnerable in your particular situation based on what your key assets are and the threat scenarios that you're facing. And then I would say the key thing is to work with your business to work out potential impacts and their likelihoods. Because, and this is something that's key in cybersecurity in general, really. It's all good and well, the cybersecurity team working in their ivory towers and saying, well, this is what could happen, and this is the, and this is the likelihood of it happening, but they don't have that business knowledge to be able to really make that assertion. So you need to work with the business to find that out. So when I've been looking at EFB problems, I've always included the pilots, because they are, they know what's going to happen in the cockpit if they get information which is wrong. So work with your business, work out the potential impacts and their likelihoods and how much it would probably cost you if something went wrong. You can then start designing and implementing mitigations to those problems. So whether it is things like alternative communication methods or RC5 implementation on your connections. It's up to you to design and implement them up to a level where you are happy with the risk. And also, where the regulator might be happy as well. And we'll talk about that in a second. Because, the best way to make sure that these mitigations are implemented is to integrate them into your regulatory approvals. So into your procedures and your checklists, into your build checklists. Make sure that you get some assurance going on in the whole operation of your drone. And for regulatory approvals, this is quite key, actually. So baking in the security into those is the best way of doing this. And then obviously create and implement a plan to audit them regularly. That comes part and parcel with regulatory approval. You can't just get approval and then go ahead and just do what you like. You need to audit that you're doing things properly anyway. And this is a shout out for the CAA Assure framework, which has been developed by the cyber oversight team at the CAA. It is absolutely excellent. It is, it has so many use cases across aviation, not just in aircraft, but airports, air traffic control towers, and drones as well. So if you're a drone operator, get your head into the CAA Assure framework. It is an excellent tool that you can use in order to look at all of these things with the support of the regulator as well. And then finally, in conclusion, so obviously MAVLink has its security limitations. Eavesdropping is easy. Attacks are probably easy as well. And I haven't even looked at the GPS and ADSB spoofing, because as we've shown with previous talks in the village, GPS and ADS-B spoofing is not difficult. And they could also have a massive effect on your drone. Particularly ones like mine, which have an ADS-B input in order to be able to sense and avoid other aircraft in the air which are transmitting the ADS-B packets. If I knew that a drone was using a flight controller like mine, then I could spoof an ADS-B packet at very low power, very, very local. So it wouldn't come up on any aircraft, but it would have an effect on the drone because it's only flying at 400 feet. So, these are other things as well that you might need to look at in terms of protecting your drones. The future and, the urban air mobility ConOps stakes are high. There's a lot of money being pumped into these industries. And in order to make sure they are safe, we have to make sure that they are secure. The two, the Venn diagram of security and safety overlap, not fully, but there's a bit in the middle where they meet. And that is where we need to make sure that security issues cannot have a safety impact. And there's some options there for future research. SMAVLink, when it comes in, I'm certainly going to be having a look at that. And then there's another thing as well I came across, the networking cryptography library has some options in there for securing radio data links over layer 2. There's some options in there I'm going to start looking at, but I didn't have time for this talk. And then finally, I just want to close out with a comment about, innovation, really, and that freedom you need in order to innovate solutions to modern day problems. And I love it. I love innovation because the ideas that get put out there and get turned into reality, it takes a certain level of magic and it's fantastic. But at the same time, so often I see them being done without any considerations of security. And as we always know in the security world, it's 10 times more expensive to implement security once a product has been developed as to baking it into the product in the first place. So, while, we still need that innovation freedom of maneuver, I still think we need to have the security considerations during the conception phase in order to, make sure we're not introducing great technology which ultimately is not that secure, and which would then cause problems later on in terms of safety risks, higher costs, and issues later on where you go down a technological route which has security difficulties like MAVLink. Anyway, that's all I've got time for today. It's very short and sweet, but I'm available for Q&A afterwards. And also, like I said, this is a series. There's going to be more coming, and there's more that you can go and look at as well in the lead up to this. Please subscribe, and I hope you will stay safe and take care.